Now you can hear me. All right. Jeez. There's always something. Okay, so in the past, I have talked about how we were going to continue talking about trends on the periodic table. In Chapter 2, we talked about atomic radius, with the smallest atoms in the upper right-hand corner of the periodic table, the biggest atoms in the lower left-hand corner. And this is due to, between the groups, between the columns, effective nuclear charge, how hard the nucleus is able to pull on the electrons. Okay, so the highest effective nuclear charge is over here. The lowest effective nuclear charge is over here. So atoms get bigger as you go from right to left. And vertically, it's due to energy level. Every step down the periodic table is a step out in energy level. The valence electrons are literally just getting further from the nucleus. Thus, the biggest atoms down here, smallest atoms up there. We're going to also deal with more trends. This time, we are going to look at ionization energy. And which mic is even... Okay, whatever. We're looking at ionization energy, electron affinity, and electronegativity. Ionization energy is the amount of energy needed to remove an electron from an atom or ion. Okay, so remember, really straightforward. You have your protons in the middle, in the nucleus, and it's surrounded by a cloud of electrons. And the reason those guys are being held together is because of, opposites attract. Okay. So in order to remove an electron, you have to put energy in. You have to pull the electron and the proton apart. Conversely, we have electron affinity. That's the amount of energy released when adding an electron to an atom. Okay, you have to put energy in to remove an electron. You get energy back out when you add an electron. So these are the same thing in opposite directions. And then finally, we have electronegativity, where electronegativity is the attraction for the shared electrons of a chemical bond. So if two atoms come together, they form a chemical bond. Obviously, the reason they're forming that bond is because they want those electrons. Both of the atoms in the bond want the electron. Some atoms want electrons more than others, and we measure that using electronegativity. So, ionization energy. It's based on the attraction between the nucleus and the electron to be removed. And we can explain differences in ionization energy in the exact same way that we explain atomic radius, using effective nuclear charge and energy levels. So greater effective nuclear charge means greater ionization energy. The harder the nucleus is pulling on those electrons, the harder they're going to be to remove. So every step you take to the right on the periodic table is going to be a greater ionization energy. So the electron is going to be harder to remove. In the exact same way as with atomic radius, energy levels. You take a step down on the periodic table, you're taking a step out and away from the nucleus. The attraction between charged particles is based on the charges of those particles, but it's also based on the distance between them. Greater distance means less attraction. So every step down is a step further out, means a lower ionization energy. So the electrons will be easier to remove. And that gives us, just a nice general trend. Greatest ionization energy up here, lowest ionization energy down here. So that same line between the upper right and the lower left is the general trend line that we're seeing, with ionization energy. Okay, the smallest atoms, the hardest electrons to remove. Biggest atoms, easiest electrons to remove. Okay, very direct, very straightforward. So, we're going to get exceptions. Okay, we didn't really talk about exceptions when it came to atomic radius. Here we absolutely are. And these exceptions are due to a half-full or completely filled subshell. Okay? So going from a half-full subshell is always going to be harder than going to a half-full subshell. Likewise, going to completely full is always going to be better than going away from completely full. Remember, this is because of degeneracy. Okay? Degeneracy is when you have multiple electrons in the same subshell. So here we have, say, 3D. We have 4 electrons. They're in different orbitals, but they're all pointing in the same direction. Because of that, you're getting lots of resonance. Okay. Okay, resonance, degeneracy, we're kind of talking about the same thing. The electrons have that same chemical or spin property, so they all look exactly the same, so they're kind of sharing space. It makes them happier. It makes them more stable. And the more you can get, the more resonance or more degeneracy there is, the happier they're going to be. So a half-full subshell, you have, in the case of the D subshell, you'll have 5 electrons all pointing in the same direction. With a completely full D subshell, you'd have 5 up, completely degenerate, and 5 pointing down, completely degenerate. So a half full or completely filled subshell is going to be happy. So taking an electron away from a half full subshell will make that atom unhappy. Whereas taking an atom away in order to get to a half full subshell will make the atom happier than you would expect. So let's compare nitrogen and oxygen. Nitrogen, hold on a second, let me open up my periodic table. Okay, so nitrogen is right here in the middle of the P block, second row. Oxygen is right next to it. Hey, puppy dog, I know you don't like the cone. But you won't stop scratching at your chin. I want your chin to get better. I'm sorry, buddy. I'm sorry. You good boy. I love you even with the cone. All right. So nitrogen is right here. It's in the 3rd column of the P block. Oxygen is right next to it, the 4th column of the P block. So nitrogen in 2p has 3 electrons, whereas oxygen right next to it has 4 electrons right there in the P block. So also 2p. So if you were to take an electron away from nitrogen, you would be taking it away from half full. You'd be taking it toward something else. But taking an electron away from oxygen, well, this electron, it has no resonance to speak of. So you're just removing repulsion. You're losing repulsion, no loss of, call it degeneracy. Okay. Whereas nitrogen, you wouldn't really be losing that repulsion. You would be losing degeneracy. Okay. So even though oxygen is one step to the right of nitrogen, it does not have a higher ionization energy. That's what you would expect. That's not what you see, because losing an electron takes oxygen to half full. Likewise, okay, so we can actually see that here. This is a chart of ionization energies for like all of the natural elements, okay? So hydrogen, you take a step to the right, helium, it gets a lot higher. The next step will take you to the next energy level with lithium, so it's a big step down. Up for beryllium, down for boron. Okay, we'll ignore that for the moment. But then carbon, then up to nitrogen, down for oxygen. Okay, so we're seeing over and over again these exceptions. So the completely full subshell, it's the exact same sort of explanation as a half-full subshell. A completely full subshell is a happy subshell. You know, whether you're talking S, P, D, etc. Okay. So here we're going from beryllium to boron. Okay. Oh, I'm covering up half the damn chart. I'm sorry about that. So here we're going from beryllium to boron. Here we're looking at nitrogen versus oxygen. Here we're looking at magnesium versus aluminum. Okay, magnesium has a full S. Aluminum has 2 S and 1 P. Okay. Here we're looking at, let's see, phosphorus to sulfur. Okay. It gets a lot more complicated when we're looking at the D block, which is why we typically don't talk about the D block when it comes to this sort of thing. Oops. So they will definitely expect you to remember the exception for the middle of the P block. You know, looking at the nitrogen column. Remember the nitrogen column. They may or may not ask you about the full subshell. Okay. So what we were talking about there was the first ionization energy. Okay, that is where it gets really popular to compare ionization energies between elements. Okay, we compare the first ionization energy of boron to the first ionization energy of carbon to the first ionization energy of nitrogen. Okay, that is what we were looking at in this chart. Okay, the first electron you remove from each element. How hard is it to remove an electron? Just the one electron. But we can also talk about removing multiple electrons. We can remove the first electron, we can remove a second electron, we can remove a third electron. So these are successive, that's what I call them, repeated ionization energies. We call it the first, the second, the third ionization energies. So electrons all have negative charge, and they all exist in a cloud outside of the nucleus. So they're all repelling one another. Okay? So the atom is kind of fluffy for that reason. Every electron you remove, there is less and less of that repulsion. The atom's getting less and less fluffy. And on top of that, the nucleus is staying exactly the same. The total number of protons remains the same. So the atom just gets smaller and smaller. It shrinks, gets less fluffy. And thus the electrons are getting closer to the nucleus. The nucleus is able to pull harder and harder on those remaining electrons. So every ionization energy is going to be higher than the ionization energy before it. Okay? The first one is going to be less than the second, is going to be less than the third, is going to be less than the fourth. But they're not all the same. Okay? This ionization energy will always be less than the next ionization energy. But sometimes you see a jump in ionization energy. And sometimes you see a huge jump in ionization energy. Okay. For example, this here is chlorine. This is all 17 ionization energies for chlorine. Okay, 1 through 17. It only has 17 electrons. This doesn't look like anything particularly impressive until you realize that this is a logarithmic graph. So this scale on the left, this isn't 0, 1, 2, 3, 4, 5, 6 joules or kilojoules or anything. This is the log, okay, meaning that we're going from 1 to 10 to 100 to 1,000 to 10,000 to 100,000 to 1,000,000. So every step on this is another power of 10, another order of magnitude. So the first ionization energy is starting at 1,000. And by the time we're done, it's close to 1,000,000. Okay, so 1,000 times higher. So as you can see from this, you are seeing increases, steady increases as you move from left to right, as you remove more and more electrons. Okay? But we do see two conspicuous jumps, one right here and one right here. Again, they don't look that impressive until you realize you're going from 10,000 to about 60,000, and then you're going from maybe 90,000 to about 500,000. Okay, so 500,000. So these are very significant increases. So why do we see significant increases sometimes and just smaller increases others? Okay. It's a little bit easier to see with this chart here, assuming YouTube lets you play at a decent resolution. Okay. So this is the third row of the periodic table, sodium all the way over to argon. The ionization energies, the first ionization energy follows the trend we've seen. It increases as we go to the right because effective nuclear charge increases as you go from left to right. Perfectly normal. And as you can see, going from top to bottom, every electron is harder to remove than the electron before. But what this red staircase is showing here is a massive increase in ionization energy when we go from blue to red. So sodium, first ionization energy is about 500. Second ionization energy is 4,500. Okay. For magnesium, it's 1450 to 7730. 2750 to 11.5. 4,400 to 16,000. 6,200 to 22,000. 8,500 to 27,000. Okay, it's just a massive increase. 3, 4, sometimes 5 times as much. What the heck is going on? Why is there that massive increase? Okay. Well, you're seeing a staircase, and you're seeing different numbers of electrons being removed. What's the difference between those elements? Okay, we have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Okay. Well, sodium has 1 valence electron, magnesium has 2, aluminum has 3, silicon has 4, etc. So we come back here, we see that 1 electron is easy to remove, 2 electrons are easy to remove, 3 electrons, 4 electrons, etc. So what this is telling us is that we're going to see a massive, massive increase when we stop removing valence electrons and start removing core electrons. Core electrons are much, much harder to remove than valence electrons. Okay? That is where we see the massive, massive increase in ionization energies. Now that they are definitely going to test you on. Okay, they're going to put that on the test somehow, some way, almost certainly, possibly. I don't know. The test, there's always more to test than can possibly be tested, so it's a little bit less certain that I'm making it, but they're very, very likely. They're very unlikely to quiz you on what follows, but I want to hammer home the quantum effects of half full and completely full. I want you to remember half full and completely full subshells. So here we see a smaller difference. If you imagine a 0 up top, then for magnesium we go from 0 to 700 to 1400. Okay, so going from first to the second, there's not really a jump. But aluminum go from 0 to 5, then 5 to 18. Okay, so that's an increase of 1300. From increase of 5 to an increase of 1300. Then from silicon, it's 750 to 1500 to 3200. Okay, so increase of 750, increase of 750, increase of 1700. So there's no jump, really. There's regular increases, but no small jump for magnesium. There is a small jump for aluminum after the first, going from the first to the second. And for silicon, there's another small jump, but it's going from the second to the third. So I've already hinted at it. Okay, we're talking about subshells. Magnesium has 2 valence electrons, and they are both in their S subshell. Aluminum has 3. The first one is in P. Okay, so the first one, was a little bit easier to remove. The second one, the reason you see that jump is because you've gone to a full subshell. Silicon has 2 electrons in its P block, so the first 2 are a little bit easier to remove, and then you see a small jump when you go down to the S subshell. So a completely full subshell, you're going to see a small increase, but it is nowhere near the same as going to a core electron. Okay, core electrons are a huge increase. For this completely full subshell, there's a slight jump. Okay, like I said, I don't think they'll test you on this because when you look at the numbers, this is pretty subtle. Okay, I had to actually go through and look at all these numbers to be sure that I knew what the hell I was talking about, right? So 0, 7, 14, 0, 5, 18, 0, 7, 50, 15, 32. Okay, I mean, it's there if you're willing to dig through the numbers, but you have to be kind of a nerd like me. We see a similar thing when we look at half-full subshells. So we can compare sulfur to chlorine, right? Actually, we can actually compare phosphorus and sulfur. Phosphorus is at the half-full subshell. It has 2 s electrons, these 2 right here, and then 3 p electrons, these 3 right here. So we can compare, the first ionization energy of phosphorus to the first ionization energy of sulfur, and we see that, unlike the trend, this is the exception. Phosphorus is 1012, sulfur is 1000. So sulfur does not have a higher ionization energy. We would expect it to be bigger. We would, in fact, expect it to be pretty, significantly bigger, but it's not there. Now, sulfur has 4 p electrons. So here's the 2s, and then 1, 2, 3, 4. These 4 are p electrons. Meanwhile, chlorine has 5 p electrons. So for sulfur, we go from 0 to 1000, then 1000 to 22. So that's an increase from 0 to 1000, then 1000 to 22 means from 1000 to 1200 increase. Chlorine, meanwhile, from 0 to 1200, from 1200 to 2300, so 12 up by 13, and then up to 38, so an increase of 15. So again, these differences are starting to get really small, really subtle increases, but they're there. That's why they probably won't quiz you on it. Like I said, the reason I want to throw that in there, because you have to remember that the half-full and completely full subshell gives you that effect, gives you that difference. So Removing the next valence electron in a subshell is going to give you just a small step. It's going to increase. Okay? Removing the first electron of the next subshell, you're going to see a small jump. Okay? You also see a small jump with the half-full, subshell. But what they're definitely going to test you on, probably, very, very, very probably, is removing the first core electron. That is where you see a huge increase in your ionization energies. Okay, so next up we have electron affinity. Electron affinity is the energy released by adding an electron. Okay, so this is the reverse of ionization energy. Ionization energy, you remove an electron. So it's the same thing, it's just in the other direction. Therefore, it is often called the zeroth ionization energy here, so i.e. sub-zero. And thus it has the same general trend as ionization energy. Now, fortunately, just for reasons, not necessarily good reasons, I don't know what they are, we never talk about subsequent electron affinities. We only talk about the one. Okay, so you don't have to worry about that. But electron affinity has the same general trend as ionization energy, and for the exact same reason. It's just a matter of how hard can the nucleus pull on those electrons. And the nucleus pulls really, really hard when you're looking at these atoms over here in the upper right-hand corner. And the nucleus does not pull very hard when you're looking at the atoms in the lower left-hand corner. Okay, these are big, fluffy atoms that don't pull on electrons. These are small, hard atoms that pull really, really hard on electrons. Okay. So the biggest atoms have the lowest ionization energies, the lowest electron affinities. These up here in the upper right have the smallest atoms, which have the highest ionization energy, the highest electron affinity. Okay. Now, electron affinity has two exceptions. Okay. First is the same exception that you got with ionization energy, going to a half-full configuration or half-full shell or completely full subshell is going to be better than going away from a half-full or completely full shell. Okay, so we're still looking at nitrogen. Okay, but we're coming from the other direction because we're adding an electron. So instead of comparing nitrogen and oxygen, we're comparing carbon and nitrogen. Okay, because adding an electron means going from carbon to nitrogen and going away from nitrogen. So carbon is really happy to be going toward nitrogen, going from the 2p electrons to 3p electrons, giving it a half-full shell. But nitrogen, you add an electron, you're taking it away from half-full, so it's unhappy to do that. So again, the general trend, you would expect nitrogen to be higher, but instead carbon is higher. Okay. And as usual, you see that, from row to row. So there's carbon and nitrogen. Here's silicon and phosphorus. So you see that all the way down. And again, they're probably not going to ask you about that outside of the P block. They could, but they probably won't. But we see another trend, namely that the second row of a group has a higher electron affinity than the first row in a group. And that goes against what you would expect. Okay? Going down the periodic table, the atoms are getting bigger, so you expect the electron affinities to be lower. But as you can see here, that's not what's happening. Fluorine has a lower electron affinity than chlorine. Oxygen has a lower electron affinity than sulfur. Okay? This violates our expectations. We have to come up with some sort of explanation for that. And the reason is because of crowding. Okay, things get crowded. We're looking at two different things. When you go down a row, you're going out an energy level. Okay? So that is why we have the trend in the first place. Going further from the nucleus means you're getting less attraction between the proton and electron, so you're getting less electron affinity. So this here represents the valence shell for our first row. This represents the valence shell for our second row. So we would expect a higher electron affinity here. Okay. But the other thing we're looking at is repulsion between electrons. Electrons are all negative. They don't like being close together. And here in the first row, you have a small valence shell, so the electrons have to crowd close together. Here on the second row, you have a much larger valence shell, so the electrons are nowhere near as crowded together. So that's what's happening. Okay, you have these two things acting in opposite directions. When you take a step down, you go out an energy level. You're losing the attraction between the protons and the electrons, but you are also losing that repulsion. This only has this effect. Okay? It only has the effect of causing the increase in electron affinity when you're going from the first row of a group to the second row of the group. After that, you don't get the bonus from decreased repulsion. It's only because this shell happens to be so small. So you only see this effect when you're looking at the second row versus the first row. Always, only, ever. Okay. So that is an exception you absolutely, again, will have to remember. They're going to expect you to remember the middle of the group, the middle of the block when you are looking at a half-full subshell. They're also going to expect you to remember the second row has a higher electron affinity rather than a lower electron affinity. Okay, so it goes up before it starts going back down. Okay, so now electronegativity. Like I said, atoms form a bond, they share electrons, they pull on those electrons because they want them. Different elements pull on those electrons with different strengths. And the strength of that pull, the measure of the attraction for the shared electrons of a chemical bond, is called electronegativity. There are like half a dozen different ways of measuring or calculating, determining electronegativity, but they are all based on ionization energy and electron affinity. Okay? Therefore, they're always going to have the same general trend. Okay? The lowest electronegativity for the biggest atoms, the highest electronegativity for the smallest atoms. Okay? So always this trend. We're always looking at this line between the lower left-hand corner and the upper right-hand corner. So fluorine up here in the upper right has the highest electronegativity of all the elements. It is ridiculous. And francium down here in the lower left has the lowest. You'll notice that the noble gases generally don't make it on this chart. Helium, neon, argon, just completely unreactive. Krypton and xenon, if you beat the ever-loving crap out of them with fluorine, you can get them to form chemical bonds. They're weak chemical bonds. They don't much like it. So you can actually measure their electronegativity. It's not something you can really do for these guys. All right. What this means is this plays a big role in a lot of different things. It plays a role in what kind of bonds the elements form, how they form those bonds, and how those bonds behave. Okay? So this is important for understanding several different things. So it's important that you remember electronegativity and electronegativity trends. Fortunately, you don't have to worry about exceptions. You just have to remember the general trend: really low over here, really high over here. So one way of thinking about it is that metals over here on the left, when they look at electrons, they see Brussels sprouts. They see, a healthy food that isn't all that tasty. It's like, okay, I get the point, but I'm not going to get excited about it. Meanwhile, the non-metals over here on the right, they look at those electrons and they really, really like what they see. They really, really want those electrons. Now, I know this reference is getting more and more dated, but this guy right here is a character called the Cookie Monster. He comes from Sesame Street, which is a children's television show on PBS/HBO. He really likes cookies. And this is a picture I got off Google when I looked for meth addict. Meth addicts don't look like that. Meth addicts are disgusting. They don't bathe. So they typically have terrible teeth and terrible skin. So this is not what a meth addict looks like. All right. The point is, non-metals really, really want those electrons. Metals really don't. So here's another way of visualizing electronegativity. This is a very popular sort of chart where they literally make it a three-dimensional rendering so that you have the lower electronegativities are physically lower and the higher electronegativities are physically higher. So you see fluorine is the highest at 4, then oxygen, then nitrogen and chlorine are tied, then you have bromine, then carbon, sulfur, and iodine are tied, then you have selenium, then you have phosphorus, right? So the nonmetals are really, really high, the metals are really, really low. And then you have the semi-metals in a line between them. Okay. You can also see some explanations for oddities among behaviors, like metals want to lose electrons. This includes all the metals here in the middle of the periodic table, but you also see that these metals have relatively high electronegativities. It's kind of weird. Gold, in particular, 2.4. That's as high as selenium or iodine or carbon, right? That explains why gold has such a low reactivity. That's why we use it in coins and jewelry, because it just has such low reactivity that it doesn't tarnish. It doesn't rust, more or less. It doesn't react to the oxygen in the air. So it just stays nice and pretty shiny gold. So that's why we call these the noble metals, because they have higher electronegativities, therefore lower reactivities. All right, so this is what brings us to the bonding triangle, or the electronegativity triangle. Or, if you're feeling kind of Dutch, the Van Alkel-Titulaar triangle, named for the Dutch guys who first, sort of came up with this little chart. On the x-axis here, we have the electronegativity. So we're bringing together two different elements, atoms of two different elements, and asking what kind of bond are they going to form. So on the bottom axis, the x-axis, we have electronegativity. So we go from low electronegativity metals to high electronegativity nonmetals. Okay, that's why we have two corners down here. We can either bring together two metals or two nonmetals. The y-axis is electronegativity difference. Okay, so that's why you only have the one corner up top, because you can only have the zero electronegativity difference when you're bringing together two atoms of the same element, or a really high electronegativity difference means you're bringing together a metal and a nonmetal. So for the very highest, that would be fluorine and francium. Fluorine with the highest electronegativity, francium with the lowest. Okay. So that's why we see these different kinds of bonds, more or less. Okay. Down here on the lower left, we have low electronegativities and low electronegativity difference. We're bringing together two elements that each have a low electronegativity. Okay? We're bringing together two metals, and appropriately, that's called a metallic bond. In this corner over here on the right, we're bringing together two elements with high electronegativities. They're both high, therefore they have a low difference between them, but they are both high. And thus, that is to say, we're bringing together two nonmetals, and that's what gives us covalent compounds. Valent because they're sharing valence electrons, co because they're sharing them. So covalent, sharing valence electrons. And then when you have a very high difference, you're bringing together a metal and a nonmetal, and that's what gives you an ionic bond. Okay. This purple region here, that's when we get to semiconductors. Those are the things you have in cell phones and computers and night vision goggles and all sorts of stuff. Really interesting chemistry. Absolutely not going to discuss it in this class. In fact, we're not even really going to discuss the metallic thing. I discuss it a little bit just so that I can compare, contrast these three different kinds of bonds. I find it's a useful thing to be able to see all three. But then we're pretty much going to abandon metallic compounds. That's alloys. Alloy chemistry, it's really interesting. It's really helpful to understand if you're going to be doing any sort of engineering, because lots and lots of different substances are made of metallic alloys. But I'm sorry, puppy dog. I know you hate your cone. I'm sorry. But metal chemistry, alloys, it's just a little bit too much for this class. So I'll be using it just to help us understand ionic and covalent compounds, and then we're going to leave it behind. We're going to be spending a lot of time talking about these two, ionic and covalent. So, finally, Brinkelhoff. Do not forget your Brinkelhoff, the diatomic elements. Okay, this is the majority of the nonmetals, bromium, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. In their pure elemental state, these guys don't exist as individual atoms. They exist as molecules, paired atoms. Okay, so when we're talking about just iodine, we're talking about elemental iodine. We're talking about molecules of iodine. Likewise, nitrogen, chlorine, hydrogen, oxygen, fluorine, all of it. And bromine. None of the nonmetals really exist as just independent atoms, but these are the ones that exist as diatomic elements. Carbon exists as either diamond or graphite. So either way, just a large extended network that can go on forever, technically. It could be infinite. Sulfur exists as 8-membered rings. So that's just kind of weird in itself. Phosphorus has 3 or 4 different forms that it can exist in. Like some of them are tetrahedra, some of them that I think have 2 phosphorus, some I think have like 6 or 8. Phosphorus is just weird. It does all sorts of weird stuff. And it's almost always incredibly reactive and highly toxic, and I think it's technically a war crime to play with phosphorus. I don't know about selenium. That's the one non-metal I don't know. I should look that up. That would be interesting. I'm not going to do it now. All right, so that's Brinkelhoff. Do not forget these guys. Unless we're talking about, if we're talking about it as part of another compound, then it's not going to be, a molecule. If we specify that we're talking about atomic iodine or atomic oxygen or something, then it's not going to be part of a molecule. If we don't specify, then it's a molecule, and we have to remember it's a diatomic element. All right, and that will do it for this first part of Chapter 3. I'm going to go grab a drink, and I'll be back in about 5 minutes for